Every time you download a file, log into a website, or send a Bitcoin transaction, something called SHA256 is quietly working behind the scenes. It's one of the most important algorithms in modern computing. But what does it actually do and how does it work? A hash function takes any input, a word, a sentence, an entire book, and produces a fixed size output. For SHA256, that output is always exactly 256 bits long. That's 64 hexadecimal characters. No matter what you feed in, you always get a 256-bit fingerprint out. A good hash function has three key properties. First, it's deterministic. The same input always gives the same output. Second, it's a one-way function. Given the output, you can't work backwards to find the input. And third, it's collision resistant. It's practically impossible to find two different inputs that produce the same output. There's also something called the Avalanche effect. Change just a single bit in the input, and roughly half the output bits will flip. The two hashes will look completely unrelated. This is what makes SHA256 so useful for detecting even the tiniest changes. So how does it work at a high level? SHA256 takes your message, pads it to a specific length, breaks it into 512-bit blocks, and then processes each block through 64 rounds of mixing. After all the rounds, the result is your 256-bit hash. Let's walk through the process. First comes preprocessing. We take the message and append a 1 bit, followed by enough 0 bits so that the total length is 64 bits short of a multiple of 512. Then we append the original message length as a 64-bit number. This ensures every message has a unique padded form. Before we start processing, we need initial hash values. SHA-256 uses 8 32-bit words as its starting state. These aren't arbitrary. They come from the fractional parts of the square roots of the first 8 prime numbers, 2, 3, 5, 7, 11, 13, 17, and 19. This guarantees there's no hidden backdoor in the initialization. Next, we build something called the message schedule. We take our 5 and 12-bit block and split it into 16 32-bit words, but 64 rounds need 64 words. So we generate the remaining 48 words by mixing earlier words together using bit shifts and XOR operations. This spreads the input bits throughout the schedule. Now comes the heart of SHA-256, the compression function. We have 8 working variables, labeled A through H, initialized to our current hash values. Each round takes these 8 variables and scrambles them using the schedule word for that round, a round constant, and several bitwise operations. Inside each round, 2 special functions do the heavy lifting. Sigma functions rotate and shift bits to create diffusion, and the choice and majority functions mix bits conditionally. The choice function picks bits from one variable or another based on a third. The majority function takes the most common bit across 3 variables. Here's what one round looks like. We compute a temporary value from the sigma function, the choice function, the current variable h, the round constant, and the schedule word. This value then shifts all 8 variables down by 1 position, with the temporary value injected at the top. After 64 rounds of this, the bits are thoroughly mixed. The 64-round constants, just like the initial hash values, come from prime numbers. Specifically, they're derived from the fractional parts of the cube roots of the first 64 primes. Again, this nothing-up-my-sleeve approach means nobody can secretly weaken the algorithm. After all 64 rounds, we add the 8 working variables back to the hash values from before this block was processed. If there are more blocks, we repeat. Once every block has been processed, we concatenate the 8 hash values, and that's our final 256-bit hash. SHA256 is everywhere. It secures passwords by storing hashes instead of plain text. It powers blockchain mining, where miners search for inputs that produce hashes with many leading zeros. It verifies file integrity, signs digital certificates, and forms the backbone of countless security protocols. That's SHA256, a deceptively simple recipe: pad, split, mix for 64 rounds, repeat. Yet this straightforward process produces a fingerprint so unique and so unpredictable that the entire digital world trusts it with its secrets.